Hi students, this is Mr. Yao. Today we're going to continue our learning about how to work with data sets. And today's lesson is about residuals. In the past two lessons, we have learned about line of best fit, and we have also learned about correlation coefficient. However, the line of best fit sometimes does not even hit any point in the data set. Then what are we going to do with the line and the data? That's kind of what we're going to learn today. But first, prior knowledge. Please pause here and try to finish question A and B. Now let's have a look. Question A. Which line below do you feel best fits the data? Give at least one reason. And for here, you can actually argue either one. So you can say, I think the first one is actually better because it's more spread out, for example. Spread out. And I can say more evenly spread out. Okay, that's one way to describe it. Or you can say it's like consistently gathered around the line. You can also argue the second one because it seems to be more concentrated. And you can say the distance from the points to the line are kind of smaller compared to the first one. Either one. So far, we haven't learned exactly how to decide that. So as long as you have a valid argument, this is kind of just a question to get you thinking. B, well, this is what we have learned in the last lesson. You're going to need to type all of the data into your calculator. And then let's review the process again. So it's going to be stat diagnostic on, okay, and then stat, then edit, then x in L1, y in L2, afterwards stat, and then calc, and then you're going to choose for lin reg, press a bunch of enter, okay, and then you're going to get the final answer. Okay, so here are the values. Oh, let me actually move these out of the way. So the first thing we did was we made sure stat diagnostic is on. Okay, and then we continue with the rest. So A is going to be negative 0.51, B is going to be 42.10, R is negative 0.89. That's why it's a strong negative correlation. And the equation is y equals negative 0.51x plus 42.1. Okay, now let's move on to define residual. We'll be finding the line of best fit under correlation coefficient, which is R, using the calculator. The correlation coefficient is a measure of how well the data fits the line of best fit. However, there is another way to analyze how well the line of best fit represents the data, and that is through something called a residual plot. First, the word residual. A residual helps us determine how far each data set is from the line. So here's how we calculate it. Because we're calculating how far they're from each other, or distance, is going to be a subtraction. So residual is the observed value minus predicted value. The observed value is what we actually see in the whole data set, which is the actual data, and this is the y value of the actual data. And then the predicted value is the y value on the line. So in other words, it is the vertical difference between the data point and the line of best fit at that given input. Here's a visual of what residual represents. So these black dots, they are the actual data points. The blue line that we see, that is the line of best fit. So we have a few different scenarios. One, of course, we could have a point exactly on the line, then the residual is just going to be 0. And then we can have a data point that is above the line. So let's say this is like around 10, and let's say this is actually at a 3, okay, for example. And actually, let's actually use the grid. So let's say that's 10, then that would make this a 6. Okay. So the data point is above the line of best fit. The data point itself is the observed value, and on the line at this point, 6, that is the predicted value, because in the previous lesson we have learned line of best fit is used to predict or make estimation. So if you actually do the subtraction, the residual would be 10 minus 6, which is a 4, and that is a positive residual. Okay, now let's look at the other one. If the point is actually below the line, so this looks like a 5, and this is a 7. Okay, and you're still using, make sure you're still using the actual data point, subtracting the point on the line. So in this case, it's going to be 5 minus 7, which is a -2, so it's a negative residual. These are the two different situations. For a positive residual, the data is above the line, making the line an underestimate. So you're given these words, but make sure you circle the correct one. You might be wondering, wait, how come when it's above the line is not over? Well, because when it's above, that means it's supposed to be a 10, but you predict it to be a 6. So you actually underestimated by 4, since it was supposed to be a 10 and you thought it's just a 6. That's why it's underestimated for positive residual. And for a negative residual, the data is actually below the line, and that means it's an overestimate because, for example, this one, it's supposed to be a 5, but you thought it's a 7, so you have overestimated by 2. So that's the kind of residual we may see. Now let's have a look at an example to see how we can calculate the residual and generate the residual plot. Example 1. This is the data set that you already got from the prior knowledge, so you can use the space above your page to actually write these down, the A, the B, and the equation. These are going to be the more important ones. Afterwards, please put all of these points on the graph. Make sure you check the labels horizontally and vertically. They're all going by 5s. You can pause here and put the points down. Okay, here are all the 9 points on the graph already. Now it's time to graph the line of best fit. All of these are not about the residuals. These are the things you have learned in the previous lessons. How you do scatter plot, and how to put the data into the calculator to generate the line of best fit, and then how to graph the line of best fit. So let's talk about this. To graph it, -0.51, well, that's not the easiest to graph, so it's basically a -0.5, which is -1/2. So the line has a slope close to -1/2. As for the y-intercept, 42.1, well, that's kind of close to 42. So here you go, we have the point. And afterwards, the issue is everything is going by 5s, so it's not the easiest to actually graph a slope of down 1 over 2. That's not the easiest, down 1 over 2. So we can't exactly do that. So in that case, let's actually change that a little bit. So let me actually use some different points. Let's change that a bit. Because everything is going by 5, so instead of doing -1 over 2, we can just rewrite the slope. Slope is the same as a -5 over 10, which means we can actually do a -5 over 10. So that means we're gonna go down 5 over 10. 42 going down 5 is still in the same relative position in each of the boxes. So you can go down by 5, then go over by 10. Go down by 5, go over by 10. So let me actually erase these points. Down 5 over 10, down 5 over 10. There you go, got that. Keep going, down 5 over 10, down 5 over 10. Around here, down 5 over 10, down 5 over 10, and lastly, down 5 over another 10. And then we can just connect all of these points to generate the line of best fit. There you go. There's our line of best fit. And that is also how we can graph it, even though we have some more difficult numbers to graph. Next, so far, we haven't touched residual yet. All we have been doing, again, is to just generate the scatter plot and graph the line of best fit. Now let's talk about the residual. So the formula to calculate residual is observed minus predicted. Okay, that means you need to know where to look for the observed value. This column is actually our observed value, because these are the actual data points. and these are the y values of the actual data points. To calculate the predicted, which is exactly what we're going to do next, use the equation you found in the starter to find the predicted value for each point. So here you go. This is the line that we got. That's our line of best fit. And the line of best fit is used to find the predicted value. For example, 13, the first number 13. We're just going to plug in all of the x values since we're looking for the predicted y values. So that's going to be y equals negative 0.51 times 13 plus 42.1. So that's what we're going to do. Plug in 13 and calculate it out. That's going to be the first predicted value. Then plug in 25, same thing. Replace the x with 25. And that's going to be negative 0.51 times 25 plus 42.1. We're going to calculate the predicted value. So please pause here and try to calculate out all the predicted values. Hopefully you have tried. So here you go. These should be the predicted values that you got. After we have found the predicted values, in order to find the residual, is going to be the observed value minus the predicted. So now we're basically taking the observed minus the predicted. So it's just 36 minus 35.47, 34 minus 29.35, 21 minus 28.84, 23 minus 23.23, and then get all the residuals. So please pause here again and try to calculate out all the residuals. Okay, hopefully you have calculated them out. Here they are. These are the residual values. Okay, so we have everything that we need, but let's quickly recap what we have done. First, we have plotted, we have generated the scatter plot by putting all the points down on the graph. Afterwards, we would type these points into our calculator so we can find a line of best fit. Then we graph that line of best fit. After that, we're going to plug all the x values into the line of best fit to find the predicted value. And then we just use the y values that are already given in the data set, subtracting the predicted values. That's going to give us the residuals. Now it's time to generate the residual plot. Now we'll graph the residual points, and to do this, we keep the same x scale that we used for the original graph, and then we label the y-axis in smaller increments based on the residual values. So as you can see in the residual values, the biggest we have is like a negative. It's a negative 7.84, and the smallest, the biggest is like a 5.79. So we just needed something between -8 and +8. So there you go. That's our graph. Horizontally, as you can see, we're still going up by 5s. But now, since we're generating a residual point, the residual plot, that means we do not need our our actual values. We also don't need our predicted values because they have served their purposes to help us find the residuals. So we're just putting down 13 and then 0.53. 13.53. Be careful because even though horizontally we didn't change, vertically we did change. It's actually going up by 2, then 4, then 6. So 0.5 is like a quarter of the box. So there you go. That's the first point. Please pause here and try to do that for all 9 points. Here you go. Hopefully you have finished. Here are the points. These are the 9 points that we got. And here's the word description of what we just did. The x values stay the same. The y values that we're trying to plot is going to be the residual values for each corresponding x value. There you go. And this is a residual plot. But you might be like, well, it looks all over the place. That's kind of what we want. A residual plot, now if you compare this plot with the one you already have on the top of the page, you might notice they have some similarity. So the residual plot is almost like a zooming in of the actual graph onto the line of best fit. And then you kind of see everything is being exaggerated a bit, like how far away they are from the line of best fit or how close they are in relative position compared to the other points. So, analyzing residual plots. When looking at residual plots, randomness is actually a good thing. Patterns in residuals are not what we want, but they can alert us to the fact that there is something going on that we need to look at more carefully. So we actually want everything to be more spread out. So uniform scatter of points indicate that regression line fits the data well. that means the line is a really good model. So when everything is actually very random or uniform, we actually like it. That is a good linear model. However, if your residual plot is a curve like this, like clearly you can see there's a curve going through that can fit that graph, a curved pattern shows that the relationship of the data is not linear, which means the data would be better represented by a non-linear model, which again means in that case, linear is not a good model. There you go. So that's everything we are going to learn in this lesson, and in the next lesson, we are going to do these by calculators. Thank you.